Okay, I'm not repeating myself. Wait a minute, are you guys there?
Yes.
Yeah, we're still here.
Okay. I accidentally, when I brought that meeting in, disable annotation, show names. Okay. When I brought the drop down or drop up in this case, it moved right before I touched it, and I hit another button, and now you guys are gone. But as long as you're here in spirit, I guess that's good enough. Okay. All right. I'll repeat just a tiny bit. Linear phased. Every element, every time, pointy top. Linear sequenced. Groups of elements. Electronic focusing, steering, flat top. Vector arrays are always steered and steered, like right and left. But unlike the phased array, which kind of sounds like the same thing, the vector arrays are in groups. Group, 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 group. So what they actually create, why is my picture, there should be like a little picture of the image shape. I just say trapezoidal, why don't they just draw a picture of it? Since it's individual groups, here, let's erase some of this. We have a beam going off in this direction. Over on this end, we had a beam going off in this direction. We have, let's see, another beam going like this. We have a beam going straight down. So you could see that what you're going to see, what we're going to see on the screen is a kind of, every time. All right, just give me purple. Purple rain. Like I'm drawing a skirt. Similar to the linear phased, which was pie-shaped, except this one, on your screen, you're going to see basically the purple here. A pie with a flat top, not a rounded bite out of it. That's the curved. Actually, you know what? Let's do something. Curved. Curved. Or convex, we want to call it. Linear sequenced. That's what we see on the screen. The original one of the multiple element ones was what the linear phased. The linear phased and then the very last one that we're just talking about now, the vector, is kind of a combo. So that's what we see on our screen with a linear vector, or I'm sorry, the vector array. And we actually, for our, you know, that old machine we have in the corner, I do believe we have a vector transducer. We could turn that on. It actually, I might turn that on anyway, because it's the only transducer that can get through my skull to look at my circle willis. So vector arrays, 120 to 250. The footprint, the entire transducer is probably pretty small on a vector. That's kind of the point of a vector, is to be similar to the phased in that it has a small footprint. It's nice for getting through the fontanelle of the skull on babies, or through the ribs or something like that. Beam steering is electronic, but it's also sequenced. So there's sequencing going across. Beam focusing is electronic. Image shape is, oh boy, now we get into that one. All right. Image shape is trapezoid, or like that. So when we go down to that table 12.4, mechanical, well, let's do something. Mechanical transducer created a sector. We're going to call this a sector. A annular phased, which is also mechanical. So it's kind of redundant. So an annular phased, let's put mechanical and annular. Annular is, that was the circle one, right? Like a target. And simply the phased. So mechanicals, transducers, and phase transducers have an image that looks like that, a sector. The linear sequential, oh wait, is that what we, yeah, they do call it linear sequential. Linear sequential, this is a rectangle. This is the linear sequential. It has a flat top because small groups of elements are firing off at any one time. So in other words, that's what you see at the top is a flat top. That's the only rectangular one, is a linear sequential. Convex is a blunted sector. We'll call this a blunt. So that's our convex, our curved. And then trapezoid is going to be created by the vector. Just remember, in convex, on the steering technique, I don't know why he wrote electronic down. When the steering, there is no steering on a convex. It looks like it's steering, but it's not. It's all the steering, including for color Doppler. There's no steering. You could angle correct, but that's not steering. You could take the color box and you can move it over here and you move it over there, and it kind of changes direction, and you think, oh, I'm steering it. No, you're not, because every beam comes straight out. It's just coming straight out of a curved surface. So like I said, I don't know why he said electronic for that as far as focusing. Boy, I don't know why chapter 12 does this. I guess I could see why. We kind of jump into some different topics in chapter 12, because we're talking about the transducers and different types of transducers. And then on page 188, we go to slice thickness. It's a very different concept. It's a resolution. We've already talked about resolutions, though. So yeah, let's go ahead and just continue to use this. I just need an enormous eraser here. Oh, that was brilliant. I needed. Let's take that one out. Oh, sorry. Let me just make another one of these in case we need it. Okay. I don't know how much we even need it now, but I don't want to draw that again if I don't have to. So let's review our resolutions. I think it's worthwhile. Axial resolution. Our ability inside of a beam to see whether or not there's two dots or one smeared out dot. If we have poor axial resolution, when we go to look at our screen, we're going to see a smeared out dot rather than two separate dots. If we have, on the other hand, so I'm going to make this a little more manageable. If, on the other hand, we have excellent axial resolution, then we will see two dots on our screen. Axial resolution, by the way, does not change. We have the same axial resolution up here as we do all the way down here. Even as the beam is spreading out and getting really horrible in the far zone, Fraunhofer zone, yeah, axial resolution stays the same because it's the length, it's 1/2 the length of the pulse, right? So that stays the same. Then we also talked about lateral resolution. If two dots are both inside one beam, actually, let me put them up here. If two dots are both inside the beam, remember that's one pulse creating an echo that is from the same exact depth. It's going to have a smeared out echo. We're not going to be able to see it as two. So that's poor lateral resolution. But as I come down more here into the focal zone, what's going to happen is the first beam, the beam that's already drawn here, is going to see that first green dot. And then the next beam is going to see the next green dot. And then we end out seeing two dots on the screen. So now we have really good lateral resolution. So far, we've been pretending, we've been in a fantasy land where the beam is infinitely thin in the depth direction. We haven't spoken about that resolution at all. That's slice thickness. So let's see if I could draw this beam. So I'm going to use these guys out here to kind of create a Well, let's start with the transducer itself, the elements themselves. As you can imagine, this element has depth to it. It's not, we've been drawing everything in 2 dimensions, but we live in a 3-dimensional world. Now, as you could see, let's use a little bit different color. Kind of a dark blue, I think. There's a whole nother dimension that we have to worry about. Just trying to give this some depth, some 3-dimensional depth to it. So, no! Oh my God, this is so frustrating. I wish there was like a button I could just snap to it. All right. Okay. So hopefully that 3-dimensional image works here. Here we have the beam width there, but we also have depth or slice thickness. So I like to sometimes I'll use the book itself as kind of a, page 188, as more like this is more like the body, right? And when we're doing ultrasound, what we're looking at are single pages. Well, we like to imagine that we're looking at single pages of the body. And so you pull that page out, and then you put that page on the screen. Makes sense? We're looking at slices of the body that go through the body. Sometimes we don't really think about what we're looking at. We're not looking at the organ. When we look at the liver, we're not looking at the outside of the liver. We're looking straight through the liver. We're looking at a page of that liver. Well, we like to think of it as a page, as this thin, this, so thin that we might as well call it infinitesimally thin. But no, it's more like about 30 pages thick. So our page is no longer really a page. That page itself has a dimension to it. And we have to be aware of this, because what happens, oh boy, I had a little diagram for myself for some, 188 did I say? Yeah, okay. It's a little hard to draw what I want to draw, so okay, I'm gonna take this guy, and I'm gonna turn the transducer so that we're now looking at this surface. All right. So if we're looking at that surface, here, what I'll do, I'll start with a side view. We're only seeing the one element because now we've changed this, and we're looking at that face is now that face. All right. So we're looking at this sideways. And let's see, I'm going to draw this in a little bit blue because that's what we had that face before. course, it's the wrong color blue because I didn't, it does, yeah, it does change elevational resolution. It has a natural focus as well, but we don't need to worry about that right now. Okay, so here's the thickness of the beam. We haven't even considered this before, but that beam, if it were perfectly thin, if it were as thin as a piece of paper, our imaging would be so much better. A lot of the times you guys are asking me like, what is all that fuzz in the blood vessel? Well, there's a number of things that causes that fuzz. One of them, though, let's draw a blood vessel in transverse. No. See, I told you it was hard. Now I got it. Here, let me zoom up. Zoom in, because I should have made this bigger. All right, slice thickness. And we have a small little vessel. Let's see, really small vessel. I'm sorry, guys, let me think. Okay. Okay. So the circle is a vessel, or perhaps a small, perhaps a small cyst. The beam we're assuming is super thin, but it's not. It's not super thin. So the beam is going through the, we'll call it a cyst, it's just easier. And let me fill in the cyst a little bit, because cysts tend to be hypoechoic, right? And blood vessels too, they should be hypoechoic. The beam is outside over there, okay. I'm just going to go ahead and fill the whole thing in because I have to. I think it's the third dimension that I'm having a hard time describing. Okay, so there's our hypoechoic vessel, hypoechoic cyst, and the beam is, for the most part, aimed right at it. Only there's a bit of a problem here, and that part of that beam is not in the cyst. Part of that beam, the dimension we don't think about, the thickness element, the thickness dimension, is actually hitting the walls of the cyst or the walls of the blood vessel, whatever, either way. Well, so we know that no echoes as this beam is coming down. No echoes are produced inside of a perfect cyst. So the sound goes through, but zero echoes. I'm just going to put a 0 here for echoes come from that cyst. That's what makes it anechoic. That's what doctors want to see, is anechoic cyst. But look at here where I drew this arrow, you know, we could just as easily show how the sound is coming down. And instead of 0 echoes, an echo is produced right at that arrowhead, because it's not fluid. It's the wall of the cyst, the vessel wall. So it's producing echoes. And so guess what that's what that means. This is inside of one pulse, one beam. So just like with lateral resolution, if you can't separate from right to left, and in this case from front to back, you get echoes, and they might not be really strong because you're only just grazing that wall with part of the beam, but it's still producing something. And so you end out with, here, let's do this color for, you end out with fuzz. Fuzz inside of the cyst, not from reverberate, well, there's some other things that happen that can cause that fuzz, but in this case, they're real echoes. They're just slightly misplaced because we weren't thinking about the fact that there's a thickness to this beam. Whew, that took me a while to get around to it, but eventually I said it correctly. Resolution is accuracy in imaging, in addition to axial and lateral. Slice thickness, also called elevational resolution, contributes to image quality. Image resolution actually deals with three-dimensional space. Shallow, deep, side to side, above and below the imaging plane. Slice thickness is measured in the direction perpendicular to the imaging plane, or above to below the imaging plane. I'm sorry, that slice thickness is measured in a direction perpendicular to the imaging plane. Okay, so I don't like, I guess it's correct. Remember, lateral resolution was perpendicular to the beam. Here's your beam. Lateral resolution is kind of the width of the beam, and how wide is your beam, and whether it's, so it's perpendicular at an angle to the actual beam. What they're saying with elevational is that it's perpendicular to the scan plane. What does that mean? The scan plane is that page out of the book. That whole page is the plane of the scan. So the thickness, the perpendicular to that, as I add pages, perpendicular is back and forth between this, from the, sugar, why would I lose my page? Oh, good, it's right there. Above to below the imaging, above to below, above, below. Okay. Yeah, I don't know about above the below, but above the below the imaging plane. In other words, just like lateral resolution was to width, elevational resolution is to depth. And he says above, below. I don't know about that terminology, but that's fine. We assume that the plane of our ultrasound image is razor thin, however, is not always correct. The beam has a measurable thickness, can vary with depth. When the slice is thick, structures above and beneath the assumed razor thin plane create reflections that appear in the image. Reflections so we expect that cyst to be black, and it's not black. Why? This is one of the reasons. Slice thickness. More about elevation and resolution, same difference. Well, what shape of active element created? What's active elements that are disc shaped? Ooh, okay, so we go back to that annular, or the disc, just a single element disc, or the annular array. They have, I believe the best. Active elements that are disc shaped provide the thinnest ultrasound slices and the best elevation resolution. In fact, so notice how I drew, what time is it? 11:21. Okay, we're gonna end on this point. Notice that, look at the shape of this beam that I drew here. If we were to look straight down the barrel of that beam, it'd be more or less rectangular. It's not perfect rectangular, but it's more or less rectangular. So the width and the depth, and I've indicated that here, are not necessarily the same. On an annular or a single element disc shaped, now, oh, I can't really draw. Well, I'm attempting to draw a beam that is round in dimensions, and so add a little, it's like a little shadowing there. That's perfect. All right, now everyone gets it. Okay, width. Okay, I kind of made that oblong. I didn't mean that, but basically width and depth are equal. Width and depth are equal. So they're round. It's a round beam. And henceforth, since it's a round beam, by the way, it also has a natural focus. Round element, round beam. And at the focus, lateral resolution and slice thickness are best at the focus. Let's see, disc-shaped crystals are found in mechanical and annular phase with just the cross-section of the circle. The height of this thickness, elevation resolution is identical to lateral resolution. What determines elevation resolution? Phased array, linear array. So on this one here, not as dramatic. The width and the depth are different. As we could see, it's not a square, it's a rectangle. At the focus, the width, of course, is best, because that's what a focus is. It's all about lateral resolution. The depth is a little bit better too. But there are ways actually. Yeah, we're going to learn in the next couple of pages. There are ways to focus the depth as well, because so far any increase in our resolution in the depth or the elevational resolution is kind of more or less accidental, because we were focusing in the lateral resolution and the width of the beam, and it just happens to do a little bit better in the depth. But there are ways in newer transducers with even more elements to actually shape that beam in two different directions at the same time and really make it come down to a focus. Which is one of the reasons why when we do have a little bit of fuzz in our what should be an anechoic structure, one of the things we could do, honestly, it doesn't usually help that much, but it is something we can do, is make sure that focus is in the right spot. If the focus is way above, you're not helping your lateral or your depth resolution. Let me just read the next page, because that's actually still a part of the same. What determines elevational resolution in phased, linear, and convex array transducers? These array probes have rectangular shaped active elements side by side. With phasing, the beam is focused or narrowed only side to side in the imaging plane, but not above and below. So This narrowing improves lateral resolution, but does not affect slice thickness. I believe it does, but with array probes, an acoustic lens is used to create a thinner slice. So an acoustic lens, we've learned so far that we can, on the older transducers, or maybe the single element transducers where you can't control with multiple elements, that we could put an internal or an external lens on. Well, we could take a linear transducer with many elements where we focus in the lateral and remember, this is just one element in a line of elements, but we're looking at it sideways now. Well, why not every element has its own focus. Now we're mechanically, with the lens, now we're mechanically focusing in that other resolution, that elevational resolution. So that's a possibility.
You sure?
Yeah, every time. What's up?
No, I said, you sure?
Yes. Why?
You didn't sound very convincing there.
Well, sometimes I have to think about this. This isn't just roll off my tongue all the time. I do have to think. The book is saying, and I believe it's simplified a little bit too much, that so far the only elevational focusing that we can get is from a external or internal lens. I believe that's simplified a little bit too much, but that's fine. We'll stick with that. So we focus electronically over here, and then mechanically in this direction. Yeah, not a good, I have a little note, not a good representation. What we're gonna learn about next time is if we do this, if we focus electronically over here with a single row of elements, why not do multiple rows of elements? And so now not only are we focusing from lateral left to right, remember this is like 1, 1, 2, 3, 2, 3, 4, 4. Outside in focuses, well, why not do this? 1, 1, 2. So now what I'm representing here is instead of a single row of elements, it's now 3 rows of elements. And the outside rows, outside rows fire before the inside rows, creating a focus again. So now we have both of these going on at the same time. Width of the beam, outside in focus, depth of the beam, outside in focus. These engineers are, I hate them. I actually really don't like engineers as No, I have my reasons for not liking engineers. And they're fine. Some of my best friends are engineers, but they drive me insane. But man, they're smart. Man, they got some good ideas. So that's we'll talk about that again next time. That's page 190, where it shows that representation. But 1132, I think I've given you enough. Friday. I really don't like taking up class time, but then I don't want to take up lab time either, because you guys are kind of, you're not getting as much lab as you should. All right, well, needless to say, well, I'll give you a time. Probably the beginning of class, we'll take a test, and then yeah, that's right. That's what I've done in the past, right? You guys are taking a test, and I'm already starting a lecture without you. I'll do that. Yeah. So that's what we're gonna do. You guys take the test at what, 10 or 10:15, I guess, because some of you will have lab in the morning. No, make it. That's right. 10:30. 10:30 test. I'm gonna start lecture without you. You can join me, or you can choose not to join me in the middle of the lecture and just follow up. I'm a couple lectures behind on posting the Zoom. I'll do that this afternoon. And then what else was I going to do? Oh, and I got to talk to a couple of you about this afternoon as well. All right. So, all right, that's it. Oh, I definitely need to stop recording in any case.